Okay, the slides are visible as well.
Yes, yes, it's quite visible. Yeah, everything seems all right. Yeah, now it's
Okay,
moving.
yeah, thank you, thank you, thanks a lot.
Okay, let Sanjit join.
Yeah, it's 1 minute to two. Sorry. Good afternoon, all. So I welcome you all once again to this afternoon scientific session. So in this afternoon scientific session, we have six number of speakers. So to begin this afternoon scientific session, may I call upon Dr. Anubam say Senorita to take over
Yes,
session chair
yes,
of
yes,
this.
Sanjit, I am here.
Okay, please uh, over to Senorita.
Okay, so shall we start right now? It's yeah, exactly it is two. We'll start. So thank you,
Yes.
Sanjit. Thank you very much, and a very good afternoon to all, to one and all here. First of all, I would like to thank all the NEMA members and organizing committee of NEMA-VII for giving me a session to be chaired. So today in this afternoon session, we will have six talk. The first talk will be by Dr. Vivas Ranjan Mazi. He will be talking on semi-classical approach to black hole thermodynamics. So first, I would like to request Dr. Vivas Ranjan Mazi to kindly present his talk. Okay, sir, you have 45 minutes, and the last 4 or 5 minutes we can think of a sort of discussion, questions, and queries. So, sir, you can please start your presentation now, sir. Please.
Yeah, thank you, Professor Senorita, and the organizing committee for inviting me to present my works here. Basically, I will present here a overview of what I am doing or what I am trying to look at or what I am trying to understand in this regime for the last 5 or 6 years. In this, I will give some details in some cases, but in some cases, I will skip the calculation. If anybody is interested, he or she can actually ask me. So basically, my interest is I will try to understand the black hole thermodynamics from a semi-classical approach. So it's not like a string theory or loop quantum gravity. It's completely a semi-classical. I will explain what is the meaning of semi-classical thing. So first of all, let me just briefly say what is a black hole. So we know that there is a space-time distance. We always consider it's like a Cartesian distance, we know. So similarly, we can have a space-time distance. And for a particular metric, you can write down in this form. And then you can ask what are the trajectories of the light. That will be determined by imposing this condition. And that will be just x equals to plus minus t in this particular coordinate system. So therefore, these lines are the 45-degree lines which the light follows. Now, therefore, this whole universe can be divided into 4 parts in this particular diagram, in this coordinate system. And we are here. So our universe is here. And all the things we can see is living here. So any two space-time events can be connected by a time-like path here. Now someone approaching towards this x equals to t line, then if one is here and if he or she wants to see what is happening here, then always you look at the light cone, and if you consider the special theory relativity such that locally the special theory relativity is satisfied, because locally we can have a flat space-time where the special relativity is the ultimate thing, then using the concept of special relativity, you can say always that everything can enter into this region. But nothing can come out, otherwise it has to be the velocity which is greater than velocity of light, which we don't allow. So therefore, everything can go into, and the opposite case is happening here. Everything can come out towards our universe. So therefore, since nothing can come out from this region, we call this as a black hole region. Even light cannot come out. Light always passes through this. And in usual case, we have a massive, highly massive object which attracts even light, and light bends and enters into it. So the black hole is a compact object or a region of space-time from which nothing can escape. Now, if it is true classically, then there is a problem in our basic physics. Bekenstein first argued that if it is true, then if any entropic object enters into the black hole region, then it seems that entropy of our universe always decreases. Because entropic objects are going into the black hole, then some of the entropy is lost inside the black hole, and it seems that entropy is decreasing with respect to our universe. But that should not be true, because in a physical process, we know that entropy should increase. So therefore, we are in a trouble if black hole cannot escape anything. Then Bekenstein argued that black holes should have some entropy. And in fact, the entropy of the black hole plus the entropy of our universe never decrease. So this is his conjecture. So he is trying to assign the entropy on the black hole horizon. Now, mathematical argument, what he gives is, it's completely analogy, that he showed that I can write down some of the mathematical quantities of the black hole in terms of the thermodynamic laws. The idea is like this. Suppose you consider the area of a particular black hole, which is Carr-Newman black hole. Area we know how to calculate. If it's a sphere, it is 4 pi r square. For Carr-Newman, something a square is here. A is the rotation per unit mass, angular momentum per unit mass. And this, if you consider the scaled area, and you take the differentiation on the both sides, that is change of the parameters by some infinite decimal amount, then you can rearranging this equation right down in this form, but these particular forms have this forms, and this particular mathematical form is similar or analogous to thermodynamic expression for the first law. So what he shows is that the black hole parameters can be connected to some thermodynamic parameter like energy, temperature, entropy, pressure, and volume by this particular way. But it is completely analogy. It's a mathematical analogy. Now, when you say that this mass can be energy, theta can be like temperature, alpha can be like entropy, then you must show that once you say these are the physical temperature and entropy, then they should satisfy the basic thermodynamical laws. What are those? Those are like zeroth law for the temperature, and the second law for thermodynamics, that is the change of entropy is always positive, entropy is increasing. So then only you can say that this mathematical analogy can be extended towards the actual thermodynamics. Another problem, another point to be noted is that you can multiply this theta by some constant and divide by this alpha by that constant. Then also this quantity is there. So therefore, it is not clear how much temperature you can actually assign here by this mathematical analogy. So therefore, this proportionality constant corresponding to this theta and alpha or the entropy should be also fixed. So these are the things we have to now look at. The first argument to assigning this alpha as a entropy comes from the increasing area law. It is given by Hawking, who showed that in any physical process, the area is always increasing. I'm not going into these mathematical details, but the basic result is the area is always an increasing quantity. So in any physical process, area is increasing. So therefore, if you call this as entropy, then this alpha, d alpha is always positive, so alpha is increasing. So you can call this as something like entropy of the black hole. But the next thing is, once you say that this area can be the candidate for entropy, then you should know what is the proportionality constant. So what he said is that he just rescale this area by this 4 pi h bar. H bar he has introduced by hand. This is from the idea that in basic physics, we know that once you calculate the entropy from the statistical description, we always look at the phase cells. And the area of the phase cell is h bar. So from that concept, he has introduced this h bar by hand just to make it dimensionless. H bar has the dimension of length square and area has the dimension of length square. So now the next target has to be to fix eta. Then these problems appear, how to fix this eta. It is not easy because we don't know what is quantum gravity. That's why he mentioned that it would be somewhat pretentious to attempt to calculate the precise value of eta without a full understanding of quantum reality of black hole. But he still tried to understand what can be the order of magnitude of eta. So he borrowed the information theory. What he did is he threw one bit of information to the black hole and he asked the question how much area has been increased. And from there, he said that if area is entropy, then from the increase of area due to the engulf of one bit of entropy, one bit of information, the connection tells you that the eta can be like this half log 2. 2 you can understand because this one bit of information, it can have two states. Therefore, this number of microstates is 2. So this 2 is appearing in this case. So he said that black hole can be entropy. Black hole can have entropy of this quantity. Now, if you use this black hole entropy here, then the temperature comes out to be this thing. Then the problem is we don't know when black hole can radiate because classically black hole can radiate. So therefore, assigning a temperature is a problem. So in one way, he is trying to assign entropy on the black hole, but the assigning temperature has a problem. After a few months, he did a calculation and from where he said that, yes, black hole has some temperature, but it's a quantum concept. What is that? This is the first semi-classical approach. Semi-classical approach means here we are not quantizing the space-time, rather we are quantizing the external fields lying on the space-time. So he took a background which represents the collapsing cell. And this collapsing cell at some point will form the event horizon of the, which represents the black hole boundary. And in this particular space-time, he quantized the scalar fields. If you solve the scalar field equation under this background, it gives birth two types of modes. One is ingoing, another is the outgoing. Ingoing in the sense is going towards the collapsing cell, and another is outgoing, means going away from the collapsing cell. Now, if some mode is coming from the past infinity towards the collapsing cell, then its frequency will be blue shifted. That we know always. And now, after passing through the collapsing cell, once the mode going away from the collapsing cell towards the future towards the future infinity, then it will suffer redshift. Now, once one can show that once this horizon formed, that redshift cannot be compensated by the blue shift, and this redshift goes as like exponential behavior. And in this case, if you define in the quantum field theory approach a particular vacuum corresponding to the ingoing mode and a particular vacuum corresponding to the outgoing mode, then the outgoing mode will see the vacuum of the ingoing mode is full of particle, and that particle has a particular spectrum, which is like your Bose distribution or Fermi distribution, depending upon the fields you are taking. And from there, you can infer that it has a temperature. So the basic idea is like this. In quantum field theory, is always decompose our scalar field into positive frequency mode and its complex conjugate. Positive frequency mode is associated with the annihilation operator. So suppose this is for ingoing mode. Similarly, you have another basis, which is the outgoing mode. That also you can write down in this way. Now, we know that one basis can be represented as a linear combination of the other basis, which is written here. Now, if beta is non-zero, if you can show that beta is non-zero, then what will happen is that this in mode with positive frequency can be written as the out mode star, and out mode star is similar to the negative frequency mode. So then, if one calculates in this case for this beta, which comes out to be non-zero, and therefore you can say that in the vacuum of in mode, the number of particles seen by the outgoing mode, because this number operator is corresponding to the out mode. So this is like a cross calculation. One can show that this is non-zero, which is proportional to mod beta square sum over all modes. And then the particle can be seen in the in vacuum with respect to the outgoing mode. And this number is coming out to be exactly in this form. From where one can say that this is the temperature. So the observer at future infinity can see particles in the in state with this distribution, and one can assign a temperature. Then this is this one. Now the fields has the temperature like this, and since the fields are in thermal equilibrium with the black hole horizon, so therefore you can say that this temperature of the horizon is also given by this. Now, if you consider instead of a collapsing cell, if you consider a static black hole, then by the same calculation, one can show that the static observer will see thermal spectrum in the vacuum of the freely falling observer, and the temperature is proportional to the surface gravity of the black hole. So therefore, this temperature, one has to look if it is consistent with the second, zeroth law of temperature of the thermodynamics or not. People actually showed that this is possible because here the zeroth law means in the space-time or on the horizon, if you go from one point to the other point, the temperature should not change because it's a thermal equilibrium. So each space-time points on the horizon should have same temperature. So now you check whether the change of kappa on the horizon with respect to the angular coordinates as well as along the generator for the horizon, if it is changing or not. One can show that this is not changing, so therefore it is consistent with the zeroth law of thermodynamics, and therefore this is the candidate for the temperature. And here, interestingly, by this Hawking calculation, one can show the exact nature of the temperature, and the h bar is coming automatically. So therefore, when you take the classical limit, which is h bar tends to 0, the temperature is 0. So this does not have any classical concept. Although it's a semi-classical calculation, why we are getting the temperature of the black hole in this form, which is the exact form. So there is no ambiguity of the proportionality constant. Now, once you know the temperature, by this mathematical identity, you can identify what will be the black hole entropy that comes out to be A by 4 h bar or 4 LP square. LP is the Planck length. So now everything is fixed. Now the next thing is you have to understand whether it is consistent with the second law. We already showed that the area is an increasing quantity. So therefore, it is consistent with the second law. So this entropy and temperature can be assigned on the black hole surface. Now, once you have this, the next question one should ask whether we can describe all this quantity from the statistical description. Till now, we don't have any statistical description or the counting of microstate for the gravity. This is a very difficult question people actually attempted in various ways, but nobody has a concrete answer or a complete answer. Here, I actually tried this or address this issue in a completely different way, in a classical way, but still it can give some hints whether we can say something about the microstates. The idea comes from the Wahl's formalism. We know that our whole gravitational theory is diffeomorphism invariant. Diffeomorphism means if you take a general coordinate transformation, x goes to xa plus some infinite decimal change in the coordinate system, then we know that the gravity action is invariant in the sense that it can be changed by at most a boundary term, and you can throw the boundary term. So therefore, gravity action has a diffeomorphism symmetry. And next thing is, since for each symmetry we have a charge, you calculate what is the charge. The charge you can calculate, the charge is coming out to be in the form of no other current JA, which can be written as a covariant derivative of some antisymmetric tensor. And if you calculate this charge on the two boundaries, one boundary is the horizon and another boundary is at the asymptotic infinity, then one can show that by calculating it on a bifurcated Killing horizon. I am not going into the details of this bifurcated technical work, but it's on the horizon of the black hole and at the infinity, then one can show that this term can be calculated as temperature into change of entropy, and this term can be identified as in this way. So it's like change in energy plus PdV term. So you can see that the entropy, which is d sigma AB or integrated of JAB, which is coming from this Noether symmetry, is a geometrical quantity, and that can be assigned to the entropy of the black hole. So the entropy of the black hole here is assigned in this form, and it corresponds to the Killing symmetry in the sense that if you consider this chi such that the metric does not change if you do this transformation, then it's a Killing symmetry. And corresponding to that chi, if you calculate this quantity, you can show that this is exactly the Bekenstein-Hawking entropy. And therefore, one can argue that the symmetries, which is like you have the Killing symmetry of the space-time, may have some role to explore the underlying microscopic description of horizon. So this comes from by this calculation that because this is calculated corresponding to the Killing symmetry. So therefore, it's like those symmetries can actually give some hints about the microstructure of the black hole entropy. Now, I went a little bit deeper into it. And first I want to mention a little bit side-aside, a little bit different topic, which is not related to the gravity. It's related to some two-dimensional conformal field theory, where one shows that if you consider the local conformal transformation, which is the symmetry of this conformal field theory, and if you calculate the charge corresponding to that, and if you calculate some quantized bracket among them, it's a Dirac bracket, then this bracket under quantization satisfies this algebra. And in this theory, if you calculate the microstates and calculate the entropy comes out to be in this form. So by calculating the microstructure of this particular theory, if you got the entropy which is like this is called the Cardy formula, because the Cardy has first calculated this one, and you see it's related to this C and the zero mode of this charge. So these are the Fourier modes of the charge corresponding to the local conformal transformation. So then it says that all the microstructure is encoded in Q0 and C. So that gives you the entropy. Now you know in quantum field theory that these scalar fields, how can they quantize? Therefore, this Q0 can be also quantized. So everything is quantized in this particular theory. But now, what has its connection with the gravity? You may ask in a opposite way. Suppose I define some bracket in this way without quantization by some way, and identify what is Q0 and C, and if you substitute in this relation, and if you see that this entropy is proportional to the area, then you may argue that, yeah, probably in gravity also this Q0 encodes all the degrees of freedom for the entropy, like here. So now we are going to in a reverse way. We start from here and try to understand if there is a microstructure or not. So this has been first addressed by Brown and Hanno, and they actually takes a particular symmetry which preserves asymptotic ADS symmetry, and corresponding to that, they calculate some charge. I will show how to define this charge. It's not like your conformal field theory. And they showed that it is, by the Cardy formula, it is exactly the entropy of the black hole. So it's a big surprise, although it is not exactly like 2D conformal field theory calculation, but here also in gravity case, we have similar structure, and therefore probably this Q naught is actually encoding some information of the black hole microstructure. So what we did is, this calculation is done at the asymptotic ADS boundary, but we are trying to assign entropy on the horizon. So it's in the opposite side of the boundary. So therefore one is to look at whether similar things is happening at the horizon as well. So this we have addressed in this particular way. We took a particular argument which is called holographic argument. I will explain what is that. Holographic argument is, we already showed that this entropy on the horizon can be assigned and the entropy is proportional to the area. So as if instead of the bulk, all the information is encoded on the area, because usually we know that the entropy depends on the volume of the system, but here the entropy is instead of volume of the black hole is proportional to the area. So as if all the information is lying on the surface. So this is kind of a holographic argument is there. The bulk is reflected, or the bulk information is reflected on the area. So therefore, what we looked at, that some of the previous results of Padmanabhan also gives this indication. He showed that the bulk part of the gravitational action can be related to the surface part of the action. Although he always throw away the surface part, but it has some importance in the gravity. And if you just calculate the surface part on the horizon, it gives back exactly the expression of entropy. And also, interestingly, although it sounds a little bit awkward, but you can actually find out Einstein's equations from the surface term alone. So all these previous results of Padmanabhan tells you that probably if you look at the surface term and do the all Virasoro type business, we can say about the microstructure of the horizon entropy. So what we did is took a particular surface term in the action, which is called Gibbons-Hawking surface term, and now you can write down this surface term or the full volume by considering the Gauss theorem, and using the same no-ether prescription, you find out what is the no-ether current. That will come in this form. I'm not going into the details, but you can find out this one. Now, next thing is you find out those diffeomorphisms which asymptotically preserves the horizon. So if you define a coordinate system and the observer says that they can see the horizon, and say that you change your coordinate system such that at the horizon, the change of GAV is 0. So it is asymptotically killing vector. And define a particular bracket by this antisymmetric combination of the Lie variation of this charge corresponding to this diffeomorphism. And if you calculate this one corresponding to this Xi, one can show that that satisfies exactly this algebra. So this is our result. And now you can identify what is C, what is Q. That comes out to be in this form. And now you substitute in the reverse way, take the Cardi formula is granted and see it is area. It comes out to be area, so it's a black hole entropy. So in the reverse way, you show that by this particular bracket, you can assign the entropy through the zero mode of the charge and the central charge, C. So then we said that, yes, probably the horizon entropy can be explained through this Q naught, and this microstructure can be explored through this Q naught. I will come to this later. But what we understand is that there is a basic difference between the conventional physics, which we learn in the MSc statistical mechanics, and its black hole horizon. In conventional physics, we always say that the degrees of freedom are absolute, in the sense that if you assign different observers, all observers will say that these are the degrees of freedom, and they will assign the same degrees of freedom for your system. And therefore, the entropy, which is related to the logarithm of the degrees of freedom, will also be absolute, and it is independent of observer. But whereas in black hole case, we just showed that we are taking those diffeomorphisms, which is a subclass of all the diffeomorphisms, which keeps your horizon structure invariant because delta GB equals to 0 near the horizon. And those observers will see the horizon always. So those diffeomorphisms only can give you that particular entropy. So it's not the all diffeomorphisms. So a particular observer will see or assign those degrees of freedom. So therefore, in this case, degrees of freedom corresponding to the related charge is responsible for the entropy is observer dependent. So there's a huge difference between the conventional physics and in black hole horizon. Here, if we can find out the degrees of freedom from this charge, then these degrees of freedom will be observer dependent. Other observer will not see these degrees of freedom. So at least we understand that if you want to give a statistical description, that statistical description can be given through Q naught, and those statistical description will be observer dependent for entropy. Now come back to the temperature. Why the black hole horizon has temperature? This is another question. Why I am asking this thing? Because we know that if you have a cylinder of gas, then the kinetic theory of gases explain the temperature of the gas. Similarly, what is the physical mechanism which is saying that there should be a temperature on the horizon? So for that, we consider a particular model. We gave a model for that. So this model is given by by us. What we consider is we wrote the Schwarzschild metric in this particular coordinate system, which is called Eddington-Frankenstein outgoing null coordinates. And we consider a massless charges particle is moving there. And horizon is given by, we know that this is equals to 0. Now this particular path of the massless particle has to be null-like or time-like, light-like, because it's a massless particle. And the tangent vector for that path are given by this one, which is perpendicular to the path of the null surface or the perpendicular to the horizon. Now for this case, if you consider the Hamiltonian of the particle, the Hamiltonian for the outgoing massless particle in the near horizon limit comes out to be in this form. This PR is the radial momentum, and R minus RH is the distance from the horizon, and the ingoing path is given by this Hamiltonian. So you have two particular Hamiltonian, one for the outgoing massless particle, one for the ingoing. Now, if you look at the outgoing Hamiltonian, it has a structure like this kappa into XP. And this kappa into XP Hamiltonian, if you go to another canonical variable or another XP, then you can write down this in the form of inverted harmonic oscillator. So therefore, this Hamiltonian has an instability because inverted harmonic oscillator at x equals to 0 has an instability. So that is reflected in the solutions of the path. If you look at the path, the solution for the position will be this, and for the radial momentum will be this. Now this radial momentum is diverges near the horizon. So near the horizon, this Hamiltonian gives you a local instability in the dynamic of the massless particle. Now next question we are asking whether this instability, which is local, you cannot visualize globally, can have some signature of the quantum level, or whether this local instability can be perceived by some quantum effect. So in addressing this question, what we did is we consider a particle which is tunneling to this particular Hamiltonian. That we calculated for this through Hamilton-Jacobi formalism. Once you calculate the wave function for that particle, it gives you a real part in the wave function that coming because this Hamiltonian has xp, and for a particular energy, P is given by h by x, and x equals to 0 is your horizon. So when the particle is crossing the horizon, at x equals to 0, this momentum has a singularity. And if you consider the singularity at the horizon, it gives you a imaginary quantity in the semi-classical action, and that gives you a real part in the wave function, and therefore you can calculate a finite probability for escaping the particle through the horizon. And similarly, for the ingoing one, you can calculate the probability, and the tunneling probability through this horizon will be like this thing. And once you compare with this, the thermal Boltzmann factor, you can identify what is the temperature of the particle seen by this particular particle, and then by the local equilibrium condition, you can say that this is the temperature of the horizon. So you see that from this particular Hamiltonian, you can assign a temperature on the horizon. And this particular Hamiltonian has a property that it is unstable on the horizon. So therefore, this local instability provides a non-zero quantum probability of escaping the outgoing particle through the horizon. And then the particle can fill the horizon as a thermal object. And therefore, we are assuming that or arguing that this local instability has a big role to give or to understand the basic mechanism which will tell that this is the mechanism for which we can see, or some particular observers see, the temperature of the horizon. With this Hamiltonian, you can do another calculation which is similar to what I explained earlier, like Hawking calculation, ingoing mode and outgoing mode. What we did is, we see if there is a wave function at some t equals to 0, how it evolves under this Hamiltonian. So it is evolves in this way. Now, if you consider a very simple wave function, which is your free particle wave function, plane wave, and if you say that it will evolve under this Hamiltonian, that means your free particle wave function or free particle is very near to the horizon, and then it will, later time it will evolve, which will be like this. Now you ask the question that if I consider the Fourier transformation of this later time wave function of the free particle under this Hamiltonian in this way, and if you can write down in this form, and you can say that this beta is non-zero, then you will say that this wave function has a mixture of positive frequency, which is this one, and negative frequency, which is this one, with respect to this particular e to the power I omega mode. So then, therefore, we want to calculate what will be the beta. If beta is non-zero, then you can say that the later time wave function has a mixture with respect to this particular thing. We calculated this one, and we saw that there is no vanishing beta. It has this particular structure. Now, why it is like a Fermi structure? If you look at the Hamiltonian, it has a first order derivative with respect to the position because it is kappa x into p. So therefore, it has a property which is like Dirac equation. So therefore, this +1 is coming. So it has a Dirac nature. And you can find out the temperature like this. So with this Hamiltonian, which is unstable in nature, once again we found that through the Hawking-like calculation that it can explain the temperature. So we conjecture that horizon creates a local instability which acts as the source of the quantum temperature of the black hole. This we established for several cases. Here we gave for Schwarzschild black hole. We did for Kerr black hole as well. Also for a generic null surface with Paddy. Unfortunately, he expired after completing the calculation. We wrote that we included his name. So it has been published recently. So let me now finish my talk by discussing what we have right now. What we understand is that black hole entropy in GR is proportional to the horizon area. So it's contrary to usual thermodynamical system, it is not depending on the volume of the system. And as if the information hiding behind the horizon is captured on the horizon. So it's like a holographic thing. And the concept of thermodynamics we understand is observer dependent. Some people will see the temperature and some people will not. Like your freely falling observer will not see the horizon and therefore he will not see any temperature or entropy, whereas the static observer will see them. What do we know so far? Degrees of freedom should be observer dependent. The charges for asymptotic structure preserving diffeomorphism may illuminate about the degrees of freedom. And temperature of the horizon can be a result of local instability. Are we far from the microscopic description? Actually, we are far from. We don't know how to quantize Q naught. But recently, few years back, we saw that this Q naught can be related to the Hamiltonian of the GAV. GAV means the background or the gravity. So probably if you can quantize Q naught, you can understand what are the degrees of freedom, and calculating them, probably you can identify the entropy. And next thing is we saw that this local instability can illuminate about the temperature. So this question is, can the instability provide a mechanism to evolve the system in thermal equilibrium? If so, what is the process? So we are expecting that this approach can give some idea about the microstructure of the black hole thermodynamics. Thank you for your attention.
Thank you, Dr. Vibhas Ranjan Mahi, for the very nice talk you have delivered. It was such an informative talk. Okay, now this is open to all the audience. If you have any question, you can either type it there in the chat box, or you can unmute your mic and directly ask the question. The audience, please.
Hello, sir.
Yes, please.
Yes, please. Sir, can you just go back to your slide number 31, where you have showed that the temperature around, of the horizon can be source for this, local instability, because of this local instability you have mentioned, right?
Yes.
Yes. 31. Okay. So, can you go just you have shown that deriving that Schwarzschild coordinate into, Schwarzschild geometry, you have written that line element in, Eddington-Finkelstein coordinate, right?
Yes.
Yes. So, what is, so then the calculation, is it coordinate dependent? If you choose Kruskal coordinate or anything other coordinates, so whether those results will be coordinate dependent or not?
Yeah, of course, because in Kruskal
Yeah, of course,
coordinate,
because
can you please unmute your mic? Yeah. So in Kruskal coordinate,
so in Kruskal coordinate, what will happen is that
it can actually cover all the space-time, full space-time it can cover. So therefore, in Kruskal observer, which is the perfect coordinate system for the infalling observer, he will not see where is x equals to t. The horizon is not visible for him. So he cannot see any temperature or anything. So if you calculate anything in these Kruskal coordinates, since it describes the full space-time, you cannot see that particular instability or the mathematical term, which is the divergent nature in the mathematical calculation, and therefore you cannot have this temperature.
Okay, sir. Thank you.
So, any other question from the audience? There is no more question in the chat box also. Okay, Dr. Vibhas Ranjan Mahi, I just have a small query.
Yeah, please.
Yeah. So somewhere in one of your slides, you have seen shown something like finding the temperature of the black hole or something like that. I have seen, I think. So I just want to know how far it agrees with the actual observational calculations which people are doing, like with data analysis and all these things, which people are estimating the temperature and all. So how far it agrees with your this semi-classical approach?
Okay. First of all, this temperature cannot be predicted by your observational data. Where observational data is actually measuring is not the temperature of the black hole horizon, rather the temperature which is coming not almost near to the horizon, but little bit far away from the horizon, the matters or anything.
Not
But
exactly
what I am
from
telling,
horizon. Yeah. From the somewhere from the disk itself, we usually with
yes, so
observational data
that
we
distance
estimate.
is not
So
like your, not exactly on the horizon. So what I am telling is the temperature of the horizon itself. It's completely a
okay,
different thing. If you look at
okay.
the
It's
temperature
for the
expression,
horizon
it is
itself.
proportional to H bar as well. So this H bar is very small quantity. Temperature therefore is very small. You cannot have a instrument which can measure this temperature. It's completely a theoretical prediction.
Okay. Yeah. Thank you. So any other question from the audience? Yeah. So since there is no more question, let us thank Dr. Bivas Ranjan Mazi once more. Thank you, sir. So
Thank
now
you.
let's move on to the next talk of today's afternoon session. The next talk is by Kavita Deka on the topic long-term X-ray flux distribution of Scorpius X1 using RXTE-SM dual and maxi observation. So I would request Kavita Deka to kindly start her talk. Kavita Deka.
Yeah, thank you, ma'am.
You can now present, and first you can share your screen and
Yes,
you can
yeah,
start.
I'm trying to share it. Just give me a moment.
Okay.
So I believe my screen is visible to all of you.
Yes, it is visible.
Okay, so I can go ahead. Good afternoon, everyone. My name is Kabita Deka. I'm a research scholar from Tejpur University and working under the guidance of Dr. Gaji Amin Ahmed and Professor Ranjit Mishra. And today I'll be talking about on this title, which is long-term X-ray flux distribution of Scorpius X1 using RXT ASM dual and maxi observation. So at the very beginning, I would like to introduce X-ray binaries. So X-ray binaries are systems which consisting of a non-collapse star and a black hole or a neutron star. So here, the Scorpius X1 is one of the brightest and persistent X-ray source in the sky, which contains a neutron star. So it was the first extrasolar X-ray source to be discovered and remains a challenging object to explain after over 50 years of study. And it is a low mass X-ray binary, and uh, many studies have revealed that SCO X1 has highly variable nature across the electromagnetic spectrum. And in the color diagram, this source exhibit a jet-shaped track, and which is why it is called a jet source. So in the next slide, I am showing this one. So it's like so in the color diagram, this low mass X-ray binary exhibit a jet shaped stroke track, which is why it is called as a jet source, which I have already mentioned. And this jet shaped track displayed three branches corresponding to three different spectral states. The upper portion of the track is known as the horizontal branch. As the source moves downward, it enters the normal branch, and then it enters to the lower portion of this track during higher X-ray flux, which is called this flaring branch. So these state sources vary on the time scales of minute to hours, which makes it a suitable source for study for flux distribution study. So for this work, our motivation is to find out different probability distribution corresponding to different spectral states while this source spends time in these three branches: horizontal, normal, and flaring branches. And to carry out this work, we have used this observation from RXTE. So from RXT, we have used this all sky monitor dual observation data for this time period, and in these two energy bands. And again, we have also used the publicly available light curve from monitors of all sky X-ray image maxi data for this time period and in these two energy band. So after obtaining the light curves, we have made histograms from that, and to fit those histograms, we have used these two probability distribution function. One is the Gaussian distribution, and the other is the log normal distribution. So what we have done, we have used the combination of these two distribution, something like this. So this combination represents two log normal distribution, combination of two log normal distribution, and again this one represents the combination of a log normal plus Gaussian distribution. And here we have also we have tried to use the combination of three log normal distribution like this, and combination of like two log normal distribution function and Gaussian, and there are two other combinations like log normal plus Gaussian and three Gaussian distribution, which we have used so far to fit those flux histograms which we have produced by using this light curve from RxD ASM and maxi data. So these are the results which we have obtained from RxD ASM dual data. So again, I would like to mention that here I have shown only the best fitted results, like the combination which has given us the best reduced chi-square value. I am showing that one only. So here we can see RxD ASM dual B-band histograms. So this histogram is well fitted with two log normal distribution function, and we have obtained this reduced chi-square for this 1.78, and this is for RxD ASM dual C-band data, which we have fitted with again using this two log normal distribution function, and the reduced chi-square we have obtained here is 1.93. And here you can see this again, the RxD B-band ASM dual B-band histogram and RxD C-band dual histogram. But here I have fitted this histogram using this combination of three log normal distribution. So here the reduced chi-square are like 1.24 for B-band and 1.11 for C-band. So we can see that when we use double log normal distribution, the reduced chi-square is slightly higher when we have used this triple log normal distribution. Similarly, this is the results for maxi. Again, I have used two double distribution to fit the histogram first. So here I am showing the results for double log normal fitting. So the reduced chi-square which we have obtained here is 0.091 and 1.27. And here, this is the histogram for again maxi B band and maxi C band using which we have fitted using triple log normal distribution. So again, we can see there is a difference between the reduced chi-square while we are using double log normal distribution, between double log normal distribution fitting and triple log normal distribution fitting. And so this one is the correlation plot between RxD B band and C band. So in this panel, I have plotted this histogram, light histogram, and in this panel, I have plotted the C band histogram, and here I have plotted the flux of B band with respect to flux of C band. So here we can see this. Here I have shown the so these are the peak values which we have obtained from earlier flux distribution fitting, so which is well correlated for these two bands. So we can see these points are like this conjunction points are like well correlated, and this is for RxD ASM dual. And so this is for corresponding to one peak, this is corresponding to the second peak, or this is corresponding to the third peak, which implies that this source has three distinct spectral states. Again, this is the results for MAXI, which we have obtained from MAXI observation. So this is also well correlated and implies that the source COX-1 has three distinct spectral states. So from this observation or from the studies, we have observed that both B and C band data for RXT and MAXI histograms are better fitted with triple log normal distribution fitting than the other combinations. And for both RXT and MAXI data, SCOX1 shows a trimodal distribution, and this suggests that the system has three distinct spectral states. And this classification based on the MAXI RXT result is consistent with the detailed spectral studies where the source shows three distinct branches, which I have already mentioned: horizontal flaring and normal branch. And again, detailed correspondence study between the states found here in our study and the different branches will be undertaken in future. And thank you so much for hearing. That's all from my side.
Okay, thank you, Kavita, for a very nice talk. So now it is open to the audience. Any question, any queries? Okay. So you can type there in the chat box, or you can unmute and directly ask the questions. Audience, please. Yes, audience, any question? Seems there is no question. If there is no question, we will go on with the next talk. Thank you, Kavita.
Okay.
So now we will proceed with the third talk of this afternoon session. The third talk will be given by Zanmezoy Sarkar, and the topic of his talk is Scientific Goals of the Solar Ultraviolet Imaging Telescope Payload on board Aditya L1. So I request Zanmezoy Sarkar to kindly present his talk.
Hello, am I audible?
Yes, you are audible.
Okay. Is my screen visible now?
Yes, it is visible.
Okay. Can you see my presentation?
Yes.
Okay, thank you. Hello everyone, my name is Janmeja Sharkar. I am a junior research fellow at Ayuka Pune, and I'm pursuing my PhD at Tezpur University. Today I'll be speaking on the scientific goals of the Solar Ultraviolet Imaging Telescope payload, the SOOT payload, on board our next, ISRO's next solar mission called Aditya L1. So Aditya L1 is going to be India's first multi-wavelength solar observatory in space, and it is going to be placed in the Lagrange 1 point of the Earth-Sun system. So this mission is a collaborative project of ISRO along with many other academic institutes in India, and the proposed lifetime is approximately 5 years. So Aditya L1 carries various payloads from different institutes. There is the VELC, Very Visible Emission Line Coronagraph, the Solar Ultraviolet Imaging Telescope SOOT that I'll be explaining over here. There is Solexis and Helios, two extra spectrometers, Aditya Solar Wind Particle Experiment, ASPEX, plasma analyzer called PAPA, and a magnetometer. The motivation for this payload SOOT, it came in a way that 60% of solar variability is seen in the ultraviolet band. However, the ground-based observation in this 200 to 315 nanometer wavelength is not possible because the atmosphere cuts out most of this ultraviolet light. So the aim was set to provide high signal-to-noise ratio images with 24/7 coverage of the sun, and to get full disk solar images in this 200 to 400 nanometer wavelength range. And that is the strategic reason why Aditya L1 is being placed in the Lagrange 1 point, so that there is no shadow time. Aditya is always observing the sun. As you can see over here, this is a spectrum of the, this is a spectrum of the solar irradiance from space. This solid line shows the spectral irradiance, shows the irradiance of the sun in space, whereas the dotted line shows the same thing from the surface of the Earth. As you can see that at around this 200, from around 200 to 300 nanometers, below that wavelength, almost no light comes into the Earth's atmosphere. The Earth's atmosphere cuts off most of it. However, that light is visible from space. That's why to make observations in this 200 to 400 nanometer wavelength, it's very necessary to send a payload to space. Ground-based observations are not possible. There is another challenge to it, that even though we are targeting this wavelength range between 200 to 400 nanometers, the problem is that over here, as you can see, this is 200 nanometers and this is 400 nanometers. Over here, the solar irradiance increases several fold. So imaging in this entire band of light is very challenging, because all the different photographing in different wavelengths within this range require very different exposure times, very different filter combinations, very different and poses many different instrumentational challenges. Because of all these challenges, the need for space science, as well as the need for high dynamic range photography, till date, there has been very limited observation within this range of temperature of the sun, that is 8,000 Kelvin to 50,000 Kelvin. However, this region of, this spectrum between 200 nanometers to 400 nanometers is very necessary to make observations of the sun, to get the idea of upper chromosphere as well as the lower transition region. As you can see over here, this is the photosphere of the sun, so that is the surface of the sun. On top of that, you have the chromosphere, and then there is a sudden jump in temperature, beyond which we have the solar corona. This is called the transition region. SOOT aims to observe the upper chromosphere altitudes and lower transition region altitudes, which is very understudied. Till now, there are very less observations from space in this wavelength range. So here comes SOOT to fill up this gap in data. So this is the SOOT payload. It has one thermal filter in front of it, and the light passes through, the light enters the optical chamber, and it hits the primary mirror, falls onto the secondary mirror, passes through the science filters, and hits the CCD. This is Aditya L1 payload. This is Aditya L1 spacecraft, and over here you can see the SOOT payload beside our VLC payload. SOOT aims to target some broad science goals. Some of them are that to understand the coupling and dynamics of the solar atmosphere, and how these the energy is channelized and transferred from the photosphere to chromosphere and then to the corona. To study the prominences of the sun and to understand the mechanisms responsible for the stability, dynamics, and eruption of solar prominences. To study solar flares, and to understand the early phases of what causes a flare, the flare trigger, and the early phase kinematics of coronal mass eruptions. And to study and to get an idea of sun climate interactions. That is, what is the effect of the sun on and the UV radiance on the upper layers of the Earth's atmosphere, and what is the long-term effects on the Earth's climate. So for this, an off-axis Ritchey-Chretien telescope design was employed, and it has a clear aperture of 146 millimeters, focal length of 3500 millimeters, and an F ratio of 24.8. So as you can see over here, this is the primary mirror of SOOT. This is the secondary mirror. There are two filters, a field corrector lens, finally the imaging CCD. So the CCD is a back illuminated teledyne E2V CCD, 4K by 4K resolution, and it gives an angular resolution of 1.4 arc seconds, and plate scale of 0.7 arc seconds per pixel. And the field of vision is 0.8 by 0.8 degrees. Now, the most important part of SOOT, the SOOT science filters. The SOOT has 8 narrowband and 3 broadband science filters, and stack of 2 filters are put to get a proper throughput in a specific spectral bandwidth. The different science filters have got different scientific goals and different scientific motivations to make observations. So the science filters are listed over here in the right hand side with their respective band passes. So the different science filters, some science filters, they are for photospheric magnetic observations, chromospheric transition region dynamics, to study sunspot dynamics, to study lower photosphere, to get an idea of the chromosphere and the steepening of acoustic waves. And broadband filters are there to understand the climatic effect of the sun and the stratospheric ozone balance. Suit also employs two basic imaging modes. One is the synoptic mode, which is the default mode of Suit, in which Suit will observe full disk images with all of its 11 science filters at a cadence of 24.5 minutes. The readout time for each frame is 16 seconds, and also an option is available for 2x2 on-chip binning. And in that case, the readout time would be 13 seconds. So as you can see over here, this is a sample image, magnesium image from IRIS spacecraft. And over here, the red line, it shows the field of vision of Suit, that what Suit will be observing. And Suit also has another imaging mode called ROI, or region of interest, in which an ROI, or a region of interest, can be defined by an user or can be automatically triggered if there is a flare in the sun by the means of an onboard algorithm. So in this case, the region of interest will be 8.2 by 8.2 arc seconds in size of 704 by 704 pixels. The readout time will be very rapid, 4-second readouts, and there will be a 40-second cadence for cycling through all the 8 narrowband filters. Now, the Suit payload is in itself very intelligent because it uses various onboard algorithms to make very effective imaging of solar flares as well as different solar activity. There is one feature, that is auto exposure control. The exposure is determined based on the total pixel counts. And if the pixel counts increase on successive images in a particular region of interest, Suit automatically reduces its exposure time so that the flaring centers are not oversaturated in the images. And then there is region of tracking. So let's say you define a region of interest on the sun, or a region of interest is triggered due to a flare. In that case, a region of interest will be set on the image, and then that will be locked with the feature. So as the sun rotates, the region of interest will also keep moving in the image. And there are various flare triggers that trigger Suit to move into flare mode and to choose region of interest and photograph the flare centers and the flare parts specifically. So there is the Solexis trigger. Solexis is this is a payload on board Aditya that is extra spectroscope, and that whenever there is initiation of a flare, the Solexis, it raises a flag for Suit and asks Suit to switch to flare mode. There is Helios trigger. Helios is another extra spectroscope that sends its raw hard X-ray data to Suit onboard computer, and that Suit uses that thing to understand what is the flux change in the X-ray band, and based on that, Suit switches to flare mode. And then there is Suit self trigger. Based on 2x2 binned images, Suit takes full disk solar images and sees if at any position on the sun a flare is developing or not. So if there is a flare developing, say there is a trigger from Solexis or Helios, so Suit itself will take these 2x2 binned images and it will check the flare is there or not. When the flare is there, it will lock onto a flare, create a region of interest, and keep tracking that flare and photograph it through at a very rapid cadence. So Suit has been designed in a way so that it can be augmented with other instruments also. So with VELC, which is a coronagraph, Suit can provide an effective 3 solar radius field of view when Suit data and VELC data is stacked on top of each other. The Suit data can also be combined with extra spectrometers like Solexis and Helios, and Suit has a similar plate scale of as that of SDO Solar Dynamics Observatory AIA as well as HMI. So Suit has a plate scale of 0.7 arc seconds per pixel. AIA has 0.6, HMI has 0.5. So using AIA and Suit data, we can get the dynamics we can study the dynamics on the sun from chromospheric to coronal altitudes, and we can get a insight to the magnetic fields using SOOT and HMI data. So we can correlate what is the effect of these magnetic fields on the sun onto the chromosphere of the sun. So as a concluding remark, Aditya L1 is India's first space solar observatory to be placed at the L1 point. SOOT will provide us with 24/7 high contrast, high SNR data in the 200 to 400 nanometer spectrum. SOOT data products will include full disk as well as ROI images. The onboard algorithms will help to capture the early phases of the solar flares, and the SOOT data can be easily augmented with other solar observatory data like SDO, Hinode, decayed mast, and will give us a multi-wavelength insight of the sun, SOOT along with other observational data that we get from other observatories. And these things will help us to enable, will enable us to strongly establish our scientific conclusions and goals. Presently, SOOT is in its assembly stage and final testing phase. So with this, I would like to end. Thank you.
Thank you, Janmay Sarkar, for the very nice talk. So now it is open to the audience. If any questions, any queries, please, audience. So any question? It seems there is no question. Okay, so if there is no question, let's thank Janmay Sarkar for his nice talk.
Thank you.
Then we will have our next talk by Faizuddin Ahmed on the topic effects of Lorentz violation by a CPT even non-minimal. So I would request Faizuddin Ahmed to kindly start his talk. Faizuddin Ahmed.
Yes, ma'am. Thank you, ma'am. Just a minute,
Okay,
I'm sharing my
kindly
slide.
start. Yeah, kindly start your talk. So is there any problem with the presentation? Faizuddin Ahmed,
Yes, ma'am.
is there any problem with the? Okay, now it is coming. Please start. We cannot hear you. Okay, Faizuddin Ahmed. Seems there is some network problem from his side. Let's just see for 1 minute and let's see what can be done. Faizuddin Ahmed, can you hear us?
Yeah, I think he is trying.
Yes, so shall we wait or shall we go on with the next one and we can ask him to present in the next?
Yeah,
Okay,
it's
now.
coming.
Okay, it's coming now.
So his slide is not seen.
Yeah, we can see his slide, but we cannot hear anything from him. So is there network problem from his side or not? We cannot say. So shall we proceed to the next one?
Hello.
Oh,
Yes,
yeah.
yes,
My
it is
audio.
visible. So you please, yeah, audible and visible. You please start.
Okay, ma'am. Thank you. Relativistic stellar particle in Lorentz vibrating effects. So I basically started from this client guided equation that is described by this equation. So Lorentz violating effects basically present in the standard model extension, which is an effective field theory, contains a standard model of particle physics, relativity, and the terms that break the Lorentz symmetry. So there are two various ways that one can study the effect of Lorentz symmetry. So one is by through a tensor field or by a vector field. So this standard model contains this Lorentz symmetry and the CPT violation term. So in 2011, people started working on the quantum dynamics of the particle, maybe in the spin half or maybe the spin zero particle. So the measured value of this coefficient for Lorentz and CPT violation in standard model has given in 2011 in this paper, Reviewed Modern Physics. So in this work, we carry out the bosonic action with this Klein Gordon, which is given by the SCPT Venn. So here KF mu has the symmetries similar to the Riemann tensor in relativity and has special properties. If we take the double trace, it will give the zero. So the modified Klein-Gordon equation under this Lorentz symmetry violation, we can write in this way. So where G is the coupling constant whose mass dimension is -2, F is the electromagnetic field tensor, and M is the rest mass of the scalar particle. So this tensor can be expressed in four 3 by
Okay,
3
Faizuddin.
matrices.
Excuse
Yes,
me,
ma'am.
Faizuddin. Your
Yes,
slides
ma'am.
are not moving. Yeah, your slides are not moving. Are you still in the first slide?
No, ma'am.
So your slides are not moving. You just adjust it first and you start talking. Yes, now it is moving. Okay, continue. Please continue.
Okay. So therefore, the tensor this can be expressed 4 by 4 matrices given by this one, and this tensor is this is given in these two paper, PRL and the PRD. So using these properties, so one can write the modified Klein-Gaussian equation under the Lorentz symmetry violation in this form, where E is the electric field and B is the magnetic field, as we know, and G is the coupling constant. So for different configuration of this electric and magnetic field, one can find the exact solutions of these equations. So we know in quantum mechanics, to get the complete information, solution of a wave equation is very important. So we consider this type of wave function. So where epsilon is the energy, L is the eigenvalue of the z component angular momentum operator, and k is a constant with the radial wave function. So if we substitute this solution or the wave function in this equation, one will arrive this radial wave equation, which could easily be solved by the various method. Maybe one can convert this one into confluent hypergeometric function, or maybe the Heon second order differential equation, or maybe some other process. So this solution of the radial gives the energy eigenvalue of this scalar particle, because this lambda will be there, so one can convert it this lambda in terms of the energy eigenvalue, which is some constant will be there, and this for radial wave function gives the scalar particle radial wave function, which we can connect it with the total wave function. So by solving this one can find the wave function as well as energy and can analyze how the energy and as well as the wave function of a scalar particle get influences in the presence of these Lorentz violating effects. So if in absence of Lorentz violating, it simply gives the standard level known values that is known very long back. So in presence of this Lorentz violating, one can see how the energy eigenvalue changes for different parameter. So one can insert it this potential also, because there are two ways one can introduce this potential. One is by the minimal substitution in this 4 vector of this Klein-Gaussian equation, and another is the by modifying the mass term. So different potentials known in quantum mechanics. Many people study this potential in non-relativistic limit as well as in relativistic limit. See, here I'm showing the relativistic limit because only a handful work has been known nowadays. Only 6 papers there which discuss the relativistic of Lorentz violating effects. So I am also working in this direction by taking some potentials, maybe in some positions of the magnetic field or electric field, to see how this energy of this scalar particle behaves behaves in presence of the Lorentz violating effect. Yes, ma'am.
Excuse me, Faisal, your presentation has gone.
Okay, ma'am. Ma'am, here is network issue, ma'am.
Okay, you just try once whether you can present it.
Is it visible,
Okay,
ma'am, now?
No, it's not there at all.
Okay.
So kindly try to share your presentation once again, please.
Okay, the audience, let's just wait for 1 minute. Let's see whether his network is giving some problem. If he is not able to present it at all, we will see what can be done. Now it's just present. Okay, we can see your presentation.
Okay, ma'am. Okay, thank you, ma'am.
Okay, please continue.
So one man can study this relativistic wave equations and the Lorentz interpolating effects by considering different potentials. So as I'm working in this direction, so this Lorentz interpolation has been investigated in different branches of physics. For example, is given here, along with in the principle of generalized uncertainty, in the context of rainbow gravity, in the context of the black hole thermodynamics, works. So these are the few references. So experimental violating effects have been in this direction to test the CT and Lorentz violation in hydrogen and anti-hydrogen that is first proposed in this paper, PRL. Then people also they proposed to test the CPT and Lorentz violation from the muonium spectroscopy. Then with the anomalous magnetic moments that is given in this paper. In penning traps, people propose to test the Lorentz violation. And in muon spin precision, that precision. So these are the way that people propose to test CPT and Lorentz violation. But till date, there has not any experimental evidence to detect this Lorentz violation. In future, if these violations is detect, then maybe it will be opens a new window to study this effective field theory in a more convenient way to understand the fundamental interactions in the nature. So this is 2 or 3 references. Thank you everyone for listening my talk.
Okay, thank you, Faizuddin Ahmed. There was interruption in between, maybe because of the network problem or something like that. Anyway, thank you for the talk you have presented. So from the audience, okay. So from the audience, any question or any query which you have, you can ask. Audience, any question? Okay, it seems there is no question. So let's move on to the next talk of this session by Ankur Gogoi on the title Light Scattering by Interstellar Composite Dust Analogs. So I would request Ankur Gogoi to kindly start his talk. Ankur Gogoi, please.
Thank you so much. I hope I'm audible to everyone. Hello, can you hear me?
Yes, it is audible.
Thank you. Okay. First of all, good afternoon to everyone. First of all, I'd like to thank the organizers for giving me this opportunity to present our work in this Northeast Meet for Astronomers, the 7th edition. So the topic of today's presentation is light scattering by interstellar composite dust analogs. So myself, Ankur Gogoi, and my collaborators are Manas Jyoti Burwa and Gaji Amin Ahmed. I am from JB College, Jorhat, in Assam, and Manas is from Jengraimukh College, is from Majuli, Assam, and Gaji Ahmed is from Tezpur University, Assam. So the talk is, the outline of the talk will be like this. So I will be introducing the topic, and we'll talk about the objectives, the experiments that we have done, and then simulations and some astrophysical, dust analogs. Then we'll discuss about the results and about some feature works. The light scattering behavior of isolated spherical and non-spherical particle or an aggregate of particles where the particle size ranges from nanometer to micrometer presents numerous theoretical and experimental challenges. These particles are normally found as aerosols, suspended particles in solutions, or as embedded particles, especially nanoparticles in optically transparent media. Now, the scattering of light may be thought of as the redirection or redistribution of light intensity that takes place when an electromagnetic wave encounters an obstacle or inhomogeneity, in a case the scattering particle. Regardless the type of heterogeneity encountered, the underlying physics is same for all the systems. Now, the light scattered by a particle or an ensemble of particle depends on a large number of parameters. Firstly, the intensity of light scattered by a particle or ensemble of particle depends on the angle between the incident and scattered radiation, the angle what we call as the scattering angle, which is equal to 180 minus the phase angle. Okay, this angular dependence is also a function of size, and in case of an ensemble of particles on the dispersion of sizes, then it depends on the shape or dispersion of shapes. That depends on the optical properties of the particles like refractive index, permittivity, absorption coefficients. Then it depends on the particle orientation with respect to the scattering plane. It depends on the wavelength and polarization state of the incident wave. It also depends on the number of particles in the scattering volume, and also depends on whether the particles are fluffy, fractal, the kind of the particles, porosity of the particles. And thus, the scattered light carries a lot of information about the scattering particle. In other words, it carries the fingerprint of the scatterer. Inversely, these fingerprints can be utilized to extract some of the physical properties of the scatterer. Therefore, it is very important to study the angular scattering dependency of small particulate matter, as such result contain information by which the particles, can be classified or even identified, and helps for, better understanding of radiation transfer through a medium containing this kind of scatterers. Now, why measurements? A number of theories have been developed in the recent past, to study the electromagnetic scattering by spherical and non-spherical particles. Various theoretical approaches, which involve in the computational techniques, were also performed. For examples, like a May theory, and then we have discrete dipole approximation, we have T-matrix method, we have separation of variable method, finite difference time domain method, finite element method. So a large number of theoretical, theories have been developed, which are very efficient. But despite the availability of such advanced numerical techniques, theoretical techniques, significant discrepancies between the experimental results and the theoretical predictions are generally observed, because the real situation in nature can be very complex. The real situation can be very complex in terms of particle size, shape. These are, real samples, and these are some model shapes. These are some simplified models. So the real situation in nature can be very complex in terms of these physical and optical properties, which cannot be modeled as accurately as they should be. Therefore, in order to improve the usefulness, performance, and quality of the light scattering theories, it is always crucial to have comparative analysis of the theoretical data with measured light scattering data for many different particle shapes and size ranges. So conversely, these measurements also need to be compared with simulations to calibrate the equipment. Thus, combination of theoretical and experimental techniques are capable of creating synergy to benefit each of them by giving useful information about light scattering from many different types of natural and artificial particulate matter. So why is scattering by interstellar dust is important? So dust particles are present, as you all know, dust particles are present everywhere in the solar system: cometary comet and tail, interstellar dust clouds, circumplanetary dust ring, asteroidal atmosphere, and aerosols of other planetary atmosphere. So such dust particles can be compact. In general, the asteroidal origin, the asteroidal dust are compact, or maybe fluffy, cometary origin. So aggregates of submicron to micron sized grains, which can be sometimes embedded in an absorbing mantle. Moreover, surfaces of planetary objects are known to be covered by finely grained particulate matter known as regolith layers. These particles in the interstellar medium and the regolith layer act as the heterogeneous media to scatter solar or stellar light, which is unpolarized in nature, and play a major role in the distribution of electromagnetic radiation throughout the galaxy. So observations and simulation of light scattered by such dust particles is necessary to deduce their physical properties of the constituent particles, and which may lead to the better understanding of the formation of the solar system. it is worth mentioning that measurement of the volume scattering function and degree of linear polarization, they can be used to estimate the parameters like size, porosity, and roughness of the dust particles. But there is a problem, that it is very difficult to collect these kind of dust particles. So in this context, the research on the properties of terrestrial dust is of great astronomical importance, as their properties are found to be similar to the properties of planetary regolith, cometary dust, etc. So interstellar extinction curve was also found to fit very well with dust grains comprising of silicate and graphite spheres with powerless, grain size distribution. Now, as far as the optical constants are concerned, the materials with astrophysical importance can be broadly divided into two classes: silicates, which have moderate optical constants, and carbonaceous materials with large value of real and imaginary part of the refractive index. Now, graphite is a kind of carbonaceous material which is absorbing in nature, and then phyllite is a kind of olivine, which is a silicate. So therefore, we have selected one carbonaceous particle and one phyllite particle, and we tried to measure and theoretically model the scattering properties of their mixture. Coming to the next slide. Okay. So what we did is that we did some light scattering measurements on these kind of particles, and then try to formulate some theoretical models and use some theoretical calculations to so that we can mimic the experimentally observed results. So we have used the light scattering, laboratory-based light scattering setup, which essentially consists of a laser source, which there are actually three laser sources: 543, 594, and 632 nanometer laser wavelengths. And then the laser is allowed to pass through optical fiber and allowed to be scattered by the samples, which are either sprayed by a dust sprayer or maybe levitated by using some levitation scheme. And the scattered light is collected by the detector and is digitized using the computer interfacing. And this is the dust sprayer. So we use a dust sprayer to spray dust samples in front of the laser beam, and then we measure the light scattering properties. So indeed, it is adopted from this paper, this concept. And regarding the samples, the graphite samples were collected from Sigma Aldrich, and the phyllite nanoparticles, phyllite microparticles were synthesized in the laboratory using a chemical route, which has been described in this paper before. So in the nebulizer, the phyllite and graphite microparticles were mixed in a ratio 1:1. So 50% graphite and 50% phyllite we took. So these, the dotted lines are the experimental, graphs, and the bold lines are theoretical ones. So we got the experimental results for these, the graphs. The top graphs are for volume scattering function, and the graphs at the bottom is for degree of linear polarization. And we tried to mimic this, try to model this experimentally observed results. And so since it is not possible to consider each and every shape, considering the high irregularity and dispersion in both shape and size, we considered 6 shapes. And we modeled these geometries by using Blender 3D, a volumetric geometry design software, which is freely available in Blender Org. And these generated 3D targets are then converted into dipole arrays by using a open source tool named DD-SCAD Convert. And again, it is available freely in nanohub.org. And after conversion, the shapes into dipole arrays, the 3D rendered representation can be realized by using a software named as ParaView. So these 3D volumetric targets are then directly incorporated into DD-SCAD 7.0 code for carrying out the computations. Okay, so these are some parameters, especially for refractive indices that we have taken for the calculations. And again, here also in the theoretical calculations, we have in this model, we have considered 50% graphite and 50% phyllite. And these are some the resultant graphs that we have observed. And these comparative analyses were done to fit the theoretical and experimental values of the scattering parameters. For example, the volume scattering function and degree of linear polarization using the size and shape average computed results. And from the plots, it can be observed that almost in all the cases, the normalized computational values are slightly higher than the experimental ones at the 3 used wavelengths, which may be due to the compositional imbalance between the highly absorbing graphite particles as compared to the firelight samples with lower values of imaginary refractive index. So the measurements were made from 10 degree to 170 degree, and the calculations are, of course, from 0 to 180 degree. So these are some preliminary measurements, and we are now trying to calculate, have calculations for some other, like compositions, like 10% graphite and 90% firelight and vice versa, and so on. So in conclusion, what we would like to report is that we tried to model the interstellar dust analogs of graphite and firelight, and studied their scattering properties at 3 incident wavelengths in the visible region. So it provides actually good approximation to the shape and size distribution of laboratory synthesized realistic dust particles supposed to be present in the interstellar medium. So at present, the experiments were made in the visible wavelengths, which do not allow the full utilization of the capabilities of DDA. So when we need to use some large size parameters, and longer or infrared wavelengths need to be included. So that is the next plan. So in addition, we would like to use, composite particles or mixtures of like amorphous carbon silicates and other silicates like forsterite, ansertite, or PAH. So in a single dust model to make it more realistic as compared to the interstellar environments. So this is what I wanted to tell. Thank you so much for your attention.
Thank you, Ankur Gogoi, for the nice talk which you have delivered. So now it is open to the audience. So any question, any query, if you have, kindly come forward and please. Any question? Audience? It seems there is no question from the audience side. So let's thank Ankur Gogoi once more. Thank you. Yeah. So now we are left with the last talk for today's session. That is by Dr. Devasis Bora on the topic gravitational waves from dark sector phase transition in the light of nanograph 12.5 year data. So I would like to request Dr. Devasis Bora to kindly present his talk.
Yeah, thank you very much. Am I audible?
Yes, sir. Yes, it is audible.
Okay. Do you see my screen?
Yes, yes. Presentation is also visible. Kindly start.
Okay. Okay. Sorry. All right. So thank you very much to the organizers for invitation. So today I will talk about some recent developments in this pulsar timing array data and some of the interpretations which we worked on in terms of some phase transitions. Let me open the pointer. Yeah. Okay. So this is the brief outline. So this is my slide number 2. I'll start with very preliminary remarks about gravitational waves. I'm sure most of the things are already clear to many of you from the last few talks. So I'll go through them quickly. It's mainly intended for the younger audience. So then I'll talk about gravitational waves from the early universe, and then I will come to the nanograph data. And then I will talk about the cosmological phase transitions, how to interpret nanograph data in terms of a cosmological phase transitions, and then connection to dark matter at the end. And then I will conclude. So let's start. So we all know about Einstein's theory of general relativity. We know that it's in comparison to Newtonian gravity, where the mass governs the force of gravity and the force tells other masses how to move. In Einstein's general theory of relativity, or the Einstein's gravity, we know that mass energy tells space-time how to curve, and the curved space-time tells mass energy how to move. Okay, and this is the basic equation, which is known as Einstein equation. On the left-hand side, it's the curvature of the metric, and on the right-hand side, it is basically the source of energy and mass, which goes into this energy momentum tensor. And this G alpha beta or G mu nu basically depends upon the second derivative of the space-time metric. Okay. So there are several predictions of Einstein's gravity or general theory of relativity. Most of them we all know. So it also predicts the existence of gravitational waves in the form of ripples in space-time. And it's very similar to electromagnetic waves, although there are some subtle differences. So we knew about this existence for a long time because Einstein formulated his theory in 1915, but it took a long time to actually detect gravitational waves, even indirectly, because of the very simple fact that gravity is very weak compared to electromagnetic interactions. So in 1974, it was indirectly discovered by Halson Taylor, which I will mention briefly. And there are many other predictions also. For example, Einstein's theory also predicts the dynamics of the universe through the Friedmann equations. So we use the FLRW metric in Einstein equation and get all the equations which tell us like how the universe is expanding, at what rate it is expanding, depending upon what is the constituent of the universe. And there are many other which have been experimentally verified to a great accuracy. So Einstein's theory worked pretty well in most of the situations. So we all know about waves. So this is the simple wave equation we have learned in school. Just a disturbance which actually can transfer energy from one place to another. And we all know about it, that we actually characterize a wave using amplitude, frequency,